Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera dan salam KMPK di hatiku. Saya mengucapkan selamat datang kepada ibu bapa dan juga para pelajar ke Kolej Matrikulasi Perak. Terima kasih saya ucapkan kepada para ibu bapa dan juga para pelajar kerana telah sudi memilih Kolej Matrikulasi Perak sebagai gerbang pengajian pra-universiti saudara dan saudari sekalian. Kolej Matrikulasi Perak sentiasa berazam dan berusaha untuk melahirkan pelajar yang mempunyai minda kelas pertama yang mampu bersaing di era revolusi industri 4.0 ketika ini. Dan juga kami sentiasa berusaha untuk menjana kemanjatan pelajar yang holistik dalam persekitaran pembelajaran yang kondusif. Saya selaku pengarah Kolej Matrikulasi Perak menaruh penuh harapan agar para ibu bapa yang hadir pada hari ini, para pelajar yang akan menjadi penghuni KMPK sentiasa mematuhi SOP yang ditetapkan oleh Majlis Keselamatan Negara, Kementerian Pendidikan Malaysia dan Kolej Matrikulasi Perak sendiri. Pastikan diri kita, anak-anak kita mematuhi penjarakan sosial dan sentiasa memakai mask bagi melindungi diri kita dengan permasalahan COVID-19. Bagaimana kita tahu, pematuhan kita kepada SOP ini akan dapat menghindar diri kita daripada diserang oleh penyakit yang amat berbahaya pada ketika ini. Pastikan kesihatan kita semua sentiasa berada dalam keadaan yang baik. Kita jaga kita. Sekian, terima kasih. Visi bahagian matrikulasi iaitu penjana unggul pelajar Bumiputera berkualiti ke institusi pengajian tinggi dalam bidang sains, teknologi dan profesional. Manakala misi bahagian matrikulasi ialah membangunkan potensi pelajar Bumiputera dalam bidang sains, teknologi dan profesional melalui pendidikan pra-universiti yang berkualiti untuk melahirkan modal insan yang cemerlang. Manakala misi KMPK adalah untuk melaksanakan pengajaran dan pembelajaran yang berkesan, persekitaran yang kondusif dan dilengkapi prasarana yang moden. Memperkembangkan potensi pelajar dalam aspek pembangunan modal intelek dan modal sosial pelajar dengan falsafah pendidikan kebangsaan. Meningkatkan kualiti sumber manusia ke tahap cemerlang. Untuk makluman para ibu bapa dan para pelajar sekalian, keluasan Kolej Matrikulasi Perak ialah 67.04 ekar. Dan daripada kolej ini menuju ke Bandar Ipoh jaraknya ialah 24 km, manakala ke bandar terdekat iaitu Pekan Gopeng sejauh 4 km. Dan Kolej Matrikulasi Perak ini merupakan kolej ke-6 yang dibina dan telah mula beroperasi pada 1 Mac 2002. Ambilan pertama ialah pada 23 Mac 2002, manakala 2020 merupakan ambilan yang ke-19. KMPK telah memulakan penerapan ISO 9001 sejak 2006 lagi. Untuk makluman tuan-tuan dan puan, setakat ini staf akademik KMPK adalah seramai 212 orang, manakala pengurusan dan staf sokongan adalah seramai 76 orang. Untuk makluman, kita bersama, terutamanya kepada para ibu bapa dan juga para pelajar. Program yang ditawarkan di KMPK ialah pengajian program matrikulasi sistem 2 semester atau lebih dikenali dengan nama SDS, dan pengajian program matrikulasi 4 semester atau dikenali dengan SES. SDS menawarkan 4 modul. Modul 1, modul 2, modul 3 dan perakaunan. Manakala SES ataupun sistem 4 semester menawarkan modul 3, modul 1, modul 2 dan modul 3. Kelebihan matrikulasi. Untuk makluman para ibu bapa dan para pelajar sekalian, kos penginapan dan pengajian selama berada di Kolej Matrikulasi Perak ataupun mana-mana kolej ditanggung sepenuhnya oleh kerajaan. Allowance wang saku sebanyak RM1,250 per semester kepada mereka yang layak. Dan mahasiswa daripada JPA juga bagi mereka yang layak. Dan juga kita mengeluarkan sijil matrikulasi. Untuk makluman tuan-tuan dan puan-puan, para pelajar Kolej Matrikulasi berpeluang untuk melanjutkan pengajian mereka sama ada ke universiti tempatan atau PTA dalam negara, ke universiti luar negara, tajaan JPA dan MARA, dan juga satu laluan khas Malaysian Digital Economy Corridor ataupun dikenali dengan nama MDEC. Untuk memastikan pelajar KMPK tidak tertinggal dengan sebarang kemudahan yang disediakan, KMPK telah menyediakan 7 buah makmal komputer, 2 buah dewan kuliah yang besar yang mampu memuatkan 250 pelajar setiap satu, 4 buah dewan kuliah yang kecil yang mampu memuatkan 100 orang bagi setiap dewan kuliah, sebuah bangunan makmal sains iaitu makmal biologi, makmal kimia dan makmal fizik. Kita juga mempunyai sebanyak 50 bilik tutoran, bangunan serbaguna iaitu bilik peperiksaan dan juga sebuah pusat sumber. Kemudahan pelajar pula, terdapat 5 buah blok asrama pelajar, sebuah surau yang dinaikkan taraf sebagai masjid yang dipanggil Masjid Al-Maghfirah, sebuah dewan yang dinamakan Dewan Sri Kinta. Kita mempunyai bilik sakit, 5 buah kafeteria yang menyediakan pelbagai makanan untuk menampung bilangan pelajar yang ditempatkan di KMPK, 1 buah mesin bank rakyat yang terletak dekat pondok pengawal keselamatan berada di hadapan pintu masuk kolej, sebuah butik amal yang menyediakan pakaian-pakaian untuk para pelajar, pakaian siswa, kompleks siswa dan anjum siswa, tempat ataupun kemudahan bagi para pelajar untuk belajar, sebuah matrik mat, terminal siswa, kedai siswa, pusat informasi pelajar, unit kaunseling dan kerjaya, kaunter haiwan pelajar, unit haiwan pelajar dan studio muzik serta kebudayaan. KMPK juga menyediakan kemudahan sukan, antaranya sebuah padang bola sepak, sebuah padang hoki, 5 buah gelanggang bola jaring, 3 buah gelanggang bola keranjang, 3 gelanggang tenis, 2 gelanggang squash, 3 gelanggang sepak takraw, 6 gelanggang badminton, sebuah gimnasium, sebuah padang petang, 2 parkos untuk kecergasan dan sebuah astaka. Kolej Matrikulasi Perak juga telah menyediakan 2 buah kereta, sebuah bas dan sebuah van untuk kemudahan pergerakan pelajar, terutamanya ke klinik dan juga keperluan-keperluan lain yang difikirkan perlu. Sekian, terima kasih.
Hello everyone. Today we are going over experiment 2, which is Acid-base titration. Determination of the concentration of hydrochloric acid solution. Let's go, everyone. Do you know how many learning outcomes in this experiment? There are 4 learning outcomes in this experiment. First is prepare a standard solution of oxalic acid. Second is to standardize 0.2 molar NaOH solution. Third is to determine the concentration of HCl solution. Fourth is to acquire the correct techniques of titration. Let's go to the theoretical background for this experiment. We are doing a few titrations. Titration is a laboratory technique used to determine the concentration of a solution using another solution with a known concentration. Next is about standard solution. Standard solution can be divided into 2, which are primary standard solution and secondary standard solution. Primary standard solution is solution that prepared by dissolving an accurately weighed pure solid of a known molar mass in a known volume of distilled water. We will prepare it in Part A. Secondary standard solution is solution that can be determined the molarity by using primary standard solution. We will do in Part B and Part C. Equivalence point is the point at which the added titrant reacts completely with electrolyte, while endpoint is the point at which indicate a change in color. There are few apparatus and chemical reagents that need to be used in this experiment. Burette, glass rod, white tile, retort stand, filter funnel, 50 ml beaker, 25 ml pipette, analytical balance, 250 ml cynical flask, 250 ml volumetric flask and 50 ml measuring cylinder. The chemical reagents used in this experiment are X molar HCl, 0.2 molar NaOH, distilled water, phenolphthalein, and hydrated oxalic acid. Let's continue with the experiment. Guide by
Hi, let's start experiment 2. Weigh to the nearest 0.0001 gram, around 3 grams of hydrated oxalic acid. Use a 50 ml beaker. Any exact value very close to 3.00 gram is fine. Add approximately 30 ml of distilled water. This is to dissolve the oxalic acid. If you find it difficult to dissolve, you can add more water to help speed up the process. Now you need to transfer the solution into a 250 ml volumetric flask. Don't forget to rinse the beaker and pour all of its content into the volumetric flask. This step ensures all solute goes into the flask. Now add distilled water up to the calibration mark. Upon reaching the mark, which is few milliliters before, use dropper to add in distilled water. This will avoid addition of excess distilled water. Remember, if you accidentally add excess distilled water, the process needs to be repeated all over again. When you have finished, stopper and shake the flask. This enables you to get a homogeneous solution. Now you can calculate the concentration of standard oxalic acid solution. Part B. This is how you wash and rinse a burette. Fill a burette with a small amount of tap water. Rotate the burette horizontally a few times. Discard the water through the stopcock. Here, you can check whether the stopcock functions properly or not. Repeat the steps before by using distilled water. This will clean the burette. Next, repeat the steps before by using the solution to be used in the titration. In this case, it is NaOH. Now fill the burette with the NaOH solution. Ensure there are no air bubbles trapped at the tip. Record the initial burette reading to 2 decimal places. The last number is either 0 or 5. Remember, it can be any initial reading, not necessarily 0. Next step, this is how you wash and rinse pipette. Draw a small amount of tap water. Use a pipette filler. Rotate the pipette horizontally few times and discard the water through the tip. Repeat the steps before by using distilled water. Now repeat the steps before with the solution to be used. That is the oxalic acid solution that you prepared in Part A. Now, pipette 25 ml of oxalic acid from Part A. To complete the pipetting process, touch the tip of the pipette to the side of the flask. However, do not push or blow the last drop at the pipette tip. It must remain in the pipette. Now add 1 drop of phenolphthalein. Place a white tile underneath the flask. This enables the color change to be clearly observed. Titrate the acid with the sodium hydroxide solution from the burette. Swirl the flask continuously. From time to time, rinse the unreacted solution on the wall of the conical flask and also at the tip of the burette. Upon reaching the end point, a temporary pink solution will appear. It fades, however, when the solution is swirled. Continue your titration, but now slowly, until a pale pink color is obtained. If you obtain a pale pink color and the color remains for more than 30 seconds, that is your endpoint. Record the final burette reading to 2 decimal places. Refill your NaOH into the burette to continue with the next titration. Repeat the whole process for 3 times. Tabulate the data in the data sheet, and you can calculate the molarity of the NaOH solution. Now part C. You are given unknown HCl solution, pipette 25 ml of the given HCl solution in which the concentration is unknown. Add 1 drop of phenolphthalein. Repeat the steps from 5 to 10 as in part B. Again, tabulate the data in the data sheet. And you should be able to calculate the concentration of HCl. That's it, people. All the best with your calculation.
Experiment is done. See you again.
Prior to Bohr, there were a number of scientists who were working on the structure of atom. Rutherford was one of them, and his model was the closest model to the Bohr model of atom. In fact, Niels Bohr had helped to overcome the problem in Rutherford's model of an atom. Rutherford's model of an atom had a major drawback that it could not explain the stability. It showed that electrons in an atom moves around a positively charged center, called nucleus. However, later on, it was found that any particle in a circular motion would undergo acceleration, and thus would lose energy. So, the electron would take a spiral path, and would finally fall into the nucleus. The atom would collapse. But this does not take place in reality. Bohr stated that electron thus moves around the nucleus in a circular orbit. While moving around the nucleus, electron does not radiate or absorb energy. The energy of an electron is quantized, which means an electron moving in an orbit can only have a certain amount of energy. Bohr explained that the energy of electrons remains fixed because they are restricted to some fixed orbits. Each of these orbits is at a fixed distance from the nucleus and is associated with a fixed amount of energy. These orbits are called discrete orbits, or also known as energy levels. These energy levels are represented by the letters K, L, M, N, or the numbers 1, 2, 3, 4, starting from the center. At ordinary condition, the electron is at the ground state, which is lowest energy level. If energy is supplied, the electron absorbs energy, and it is promoted from lower energy level to a higher energy level, called excited states. The electron is excited. Electron at its excited states is unstable. It will fall back to lower energy level and releases a specific amount of energy in form of light. The amount of energy released by the electron is called a photon. Photon is emitted in the form of radiation with appropriate frequency and wavelength. Let's recap. Bohr's atomic model. Postulate 1. Electron move in a circular path or orbit around the nucleus of an atom. The electron does not radiate or absorb any energy. Postulate 2. The energy of an electron is quantized. An electron moving in an orbit can have only a certain amount of energy. Postulate 3. At ordinary condition, the electron is at the ground state, the lowest level. If energy is supplied, electron absorbs the energy and promoted from lower energy level to a higher one. Electron is excited. Postulate 4. Electron at its excited states is unstable. It will fall back to lower energy level and releases a specific amount of energy in form of light that is called photon.
In 1665, Isaac Newton was a young scientist studying at Cambridge University in England. He was very interested in learning all about light and colors. One bright sunny day, Newton darkened his room and made a hole in his window shutter, allowing just one beam of sunlight to enter the room. He then took a glass prism and placed it in the sunbeam. The result was a spectacular multicolored band of light, just like a rainbow. The multicolored band of light is called a color spectrum. Newton believed that all the colors he saw were in the sunlight shining into his room. He thought he then should be able to combine the colors of the spectrum and make the light white again. To test this, he placed another prism upside down in front of the first prism. He was right. The band of colors combined again into white sunlight. Newton was the first to prove that white light is made up of all the colors that we can see. Later on, chemists and physicists have studied the characteristics of emission spectra, which consists of continuous spectrum and line spectrum. Now, let us study how the continuous spectrum and line spectrum are formed. A continuous spectrum is a spectrum that consists of all series of electromagnetic wavelengths. It is produced by incandescent solids, liquids, and compressed gases. A line spectrum is a spectrum that consists of radiation of discrete lines with a specific wavelength or frequency. It is composed of only a few wavelengths, giving a series of discrete lines separated by blank areas. When white light from an incandescent lamp is passed through a slit, then a prism, it separates into a spectrum. The white light spread out into a rainbow of colors produces a continuous spectrum. The spectrum is continuous, where all wavelengths are present, and each color merges into the next without a break. Let us consider, for the following experiment, for studying the images spectra of atoms and molecules. These are the apparatus used for the experiment. It starts with the discharge tube is filled with hydrogen gas. When a high voltage of electrical discharge is supplied, the hydrogen molecules decomposed into hydrogen atoms. The electron in hydrogen atoms absorb the energy, and it is promoted from lower energy level to a higher energy level. This energy level is called excited state. The electron at the excited state is unstable, and it will fall back to a lower energy level, and release a specific amount of energy in a form of light. The emitted light will pass through a slit. Then, it is separated into its component colors by a prism. Each component color is focused at the definite position according to its wavelength. Its form a colored image on a photographic plate. The colored image are called spectral line. Let's look at electronic transition responsible for the observed line spectrum. When an electron drops from higher energy levels or lower energy level, a photon is given off in the form light. During the electronic transition, light is emitted on a visible region of electromagnetic spectrum.
The electromagnetic spectrum covers the range of wavelengths from 10 to the power of minus 16 to 10 to the power of 8 meters, which corresponds to the frequency range from 10 to the power of 24 to 1 cycles per second. Going from the shortest to the longest wavelength, the electromagnetic spectrum includes gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, microwaves, FM and AM radio waves, and finally long radio waves. Visible light is only a small portion of the electromagnetic spectrum of wavelengths ranging from 4 times 10 to the power of minus 7 to 7 times 10 to the power of minus 7 meters. That is, from 400 to 700 nanometers.
According to Bohr's fourth postulate, when an atom makes a transition from the higher energy state to a lower energy state, the energy is radiated in the form of a photon, having a certain frequency and wavelength. The spectral lines are formed from the transition of electrons of an atom from higher energy states to a definite energy state, form a spectral series. The various spectral series of hydrogen atom can be represented with the help of energy level diagram of an atom, as shown in the animation. When an electron makes a transition from higher energy level to the first energy level, occurs in the atom, Lyman series line is obtained. The values of frequencies obtained in this transition lie in the ultraviolet region of the electromagnetic spectrum. When an electron moves from higher energy level to the second energy level, Balmer series line appears. The values of frequency is obtained in this transition lie in the visible light region of the electromagnetic spectrum. When the destination level is the third energy level, it obtained Passion series line. The values of frequencies obtained in this transition lie in the infrared region of the electromagnetic spectrum. When it is the fourth energy level, it has bracket series line, where the values of frequencies obtained lie in the infrared region of the electromagnetic spectrum. The fifth level correspond to Foon series of line, where the values of frequencies obtained lie in the infrared region of the electromagnetic spectrum. Therefore, there are 5 series of line spectrum, that is, Lyman series, Balmer series, Passion series, Bracket series and Foon series.
Series of line spectrum is a group of spectral lines formed as a result of the transition of an electron from any higher energy level to a lower energy level.
Bohr's model views the hydrogen atom as a miniature solar system, in which electrons circle around a positively charged nucleus in orbits of fixed size and energy. As we have already seen, this simple model allowed us to calculate the energy of the electron in every accessible orbit. Consequently, we were able to predict the positions of spectral lines in the atomic emission spectrum of hydrogen.
According to the second Bohr's postulate, the energy of an electron is quantized, which means an electron moving in an orbit can have only a certain amount of energy. The energy of the electron in its level can be calculated by using the following equation. The negative sign in the equation is an arbitrary convention, signifying that the energy of an electron in the atom is lower than the energy of free electron, which is an electron that is infinitely far from the nucleus. The energy of the free electron is arbitrarily assigned a value of 0. As the electron gets closer to the nucleus, En becomes larger absolute value, but also more negative. The most negative value is reached when n equals 1, which corresponds to the most stable energy state, that is called ground state, or the ground level. The stability of electron diminished for n equals 2, 3, and so on. Each of these level is called an excited state, or excited level. Bohr's theory enables us to explain the line spectrum of the hydrogen atom. Radiant energy absorbed by the atom causes the electron to move from a lower energy level to a higher energy level. Conversely, radiant energy in the form of a photon is emitted when the electron moves from a higher energy level to a lower energy level. The amount of energy needed to move an electron in the Bohr atoms depends on the differences in the initial and final states. By applying the previous equation to the emission process in a hydrogen atom, let us assume that the electron is initially at the excited state, characterized by the symbol of Ni. During emission, the electron drops to a lower energy level, characterized by the symbol Nf. The difference between the energies of the initial and the final states can be calculated by using the following equation. When a photon is emitted, the delta E is negative, which indicates the energy lost to the surrounding. The energy difference can also be calculated by using the following equation. As the transition results in the emission of a photon of frequency and energy, we can write We can calculate the energy absorbed by the electron by using this equation. When energy is absorbed, the delta E is positive. The photon is emitted in the form of radiation, with appropriate frequency and wavelength. Hence, its frequency and wavelength can be calculated by using Rydberg equation can be used to calculate the wavelength of transition of electron between two energy levels. Please note that the value of the Rydberg constant is different for both equation.
Neon lights are colorful, bright, and reliable, so you see them used in signs, displays, microwave detectors, electronic equipment, and even on the historical building. Have you ever wondered how they work, and how different colors of light are produced? The neon lamp is a type of gas discharge lamp. When an electric voltage is applied to the electrodes, enough energy is supplied to remove an outer electron from the neon atoms. If there is not enough voltage, there will not be enough kinetic energy for the electrons to escape their atoms, and nothing will happen. The positively charged neon atoms are attracted to the negative terminal, while the free electrons are attracted to the positive terminal. So, where does the light come from? Atoms in the tube are moving around, hitting each other. They transfer energy to each other, plus a lot of heat is produced. While some electrons escape their atoms, others gain enough energy to become excited. This means they have a higher energy state. The electron can return to its original energy, the ground state, by releasing that energy as a photon of light. The color of the light that is produced depends on how far apart the excited energy is from the original energy. So, Each excited electron of an atom releases a characteristic wavelength of photon. In other words, each excited noble gas releases a characteristic color of light. For neon, this is a reddish-orange light. Chlorine vapor lamp produces green, hydrogen produces blue light, sodium forms yellow light, whereas mercury gives white light, and nitrogen produces red light. Art Deco architecture is synonymous with neon lighting. Thankfully, today we have much better options than traditional neon to help maintain the Art Deco culture. The answer lies within the new solution to an old problem. LED neon lighting solutions have revolutionized the Art Deco style by making it more lightweight, low energy, and environmentally kind than ever before. Many LED neon strips work like the new LED Neon Flex, a strip of light that has amazing flexibility and customization.
Knowing the energy of every electron orbit in Bohr's model allows us to construct an energy level diagram for the hydrogen atom. You have already seen a similar diagram when discussing the origin of the hydrogen spectral line series, from Lyman to Pfund. A positive proton and a negative electron attract each other. Therefore, the energy of their mutual interaction is strongest when the electron is in the first orbit and they are closest to each other. The larger the orbit, the higher the energy of the electron, because a portion of energy must be supplied to overcome the proton-electron attraction. Note that the energy levels become closer together as the quantum number of the orbit increases, and eventually an energy continuum is reached. In the continuum, there is no attraction between the proton and the electron. The electron is free to move, escaping the positively charged nucleus. This process is called ionization. When we look at the energy level diagram, it is clear that in order to achieve ionization of the atom in its ground state, we must supply the necessary portion of energy, that is, sufficient to excite the electron to the continuum state. This energy is termed ionization energy.
Ionization energy is the minimum energy needed for the complete removal of an electron from a gaseous atom or ion in its ground state. The unit of ionization energy is kilojoule per mole. An atom is ionized when an electron is removed from n equal 1 to n equal to infinity. The value of ionization energy can be calculated by using the following equation.
You are already familiar with the equation for the energy of the electron in an orbit of quantum number n, where Rh is a constant derived from Planck's constant, the mass and charge of the electron. The value of Rh is 2.18 times 10 to the power of -18 joules. Therefore, the energy of the electron in the ground state is minus 2.18 times 10 to the power of minus 18 joules, while the energy of the free electron in the continuum is. The difference in energy between these two states is. Therefore, the ionization energy of the hydrogen atom is 2.18 times 10 to the power of minus 18 joules. Notice that the ionization energy is the same as the RH constant, and is equal to the ground state energy, but with the opposite sign.
Now let us calculate the ionization energy of hydrogen, expressed in joules per mole, and compare it with the experimentally determined value. The ionization energy of a single hydrogen atom is. You already know that the value of Avogadro's number Na tells us how many particles there are in 1 mole of the element. This means that 1 mole of hydrogen contains 6.022 times 10 to the power of 23 molecules, since hydrogen exists as molecules, H2. Therefore, the ionization energy of hydrogen expressed in joules per mole is. This theoretical value corresponds very well with hydrogen's ionization energy determined experimentally, which is 1,312 kilojoules per mole. Very good matching of the theoretical and experimental values of ionization energy confirms that the simple Bohr atomic model is quite useful in predicting the actual properties of hydrogen.
Ionization energy is determined by detecting the wavelength of the convergence point. Eventually, the line becomes so close to each other that merge at a point that is called convergent limit. At this point, the nucleus can no longer hold the electron. The electron has zero energy and freely to move. Therefore, the convergent limit is on the left-hand side, whereas the first line is on the right. Ionization energy is the minimum energy needed for the complete removal of an electron from a gaseous atom or ion in its ground state. The unit of ionization energy is kilojoule per mole.
Bohr's atomic model was the first step in understanding how the atom is built, and it gave insight into the nature of the line spectra emitted by gases. At the time, the riddle of atomic structure seemed to be solved.
Bohr was successful in introducing the idea of quantum energy and in explaining the lines of the hydrogen spectrum. However, his theory could not be extended to predict the energy levels and spectra of atoms and ions with more than one electron.
The model applied accurately only to one electron systems, the hydrogen atom, and ions such as helium-1+ and lithium-2+.
Modern quantum mechanics retain Bohr's concept of discrete energy states, and energy involved during the transition of electrons, but totally reject the circular orbits he introduced. De Broglie proposed that small particles of matter, such as electron, has a dual nature and possesses both wave and corpuscular or particle properties. We can associate wave to any moving particles. If electron have wave-like motion and restricted to orbit at fixed radii, therefore, the electron have only certain possible frequencies and energies.
Particles of light, called photons, have an energy E proportional to the frequency of the light wave, expressed by the following equation, where h is the proportionality constant known as Planck's constant, and is equal to 6.63 times 10 to the power of minus 34 joules times seconds. Because light frequency is related to its wavelength by this equation, we have, on the other hand, the energy of a particle of effective mass m, moving with the speed of light c, is given by Einstein's famous equation. Equating these two gives, and this equation relates the wavelength to the effective mass of photon.
According to Heisenberg's uncertainty principle, it is impossible to know, simultaneously, both the momentum, p, that defined as mass times velocity, and the position of a particle with certainty. Heisenberg stated mathematically, where del2 x is equal to uncertainty in measuring the position. Delta P is equal to uncertainty in measuring the momentum, and h is equal to Planck constant.
2.2 Absolute values. 2.2a Properties of absolute values. In mathematics, the absolute value or modulus of a real number x, denoted like this. First, definition of absolute value is like this, where the absolute value is divided into two, namely, positive x and negative x. For positive x, is only for x values greater than or equal to 0. Meanwhile, for negative x, is only for x values less than 0. For example, the absolute value of 3 is 3, and the absolute value of negative 3 is also 3. Is the non-negative value of x without regard to its sign. Therefore, absolute values is always positive. Please keep this in mind. Secondly, the absolute value of a number may be thought of as its distance from 0. We take example of the absolute value of 3 and the absolute value of negative 3 before, where the value of both is the same, which is 3. If we sketch it on the number line, it represents a distance of 3 units to the right and 3 units to the left from the origin. Therefore, the absolute value represents the distance of a point on the number line from the origin or 0. Thirdly, since the square root symbol represents the unique positive square root, when we applied to a positive number, it follows that absolute value of x is equal to square root of x square. For example, absolute value of 3 is equal to square root of 3 square. And absolute value of negative 3 is equal to square root of negative 3 square. 2.2a Properties of absolute values. The absolute value has the following fundamental properties, where a and b are real numbers. We may let a is equal to 3 and b is equal to negative 2. A absolute value of a is greater than or equal to 0. For example, absolute value of 3 is greater than or equal to 0. B absolute value of negative a is equal to absolute value of a. For example, absolute value of negative 3 is equal to absolute value of 3, which is equal to 3. C absolute value of a plus b is equal to absolute value of b plus a. For example, absolute value of 3 plus negative 2 is equal to absolute value of negative 2 plus 3, which is equal to 1. D absolute value of b minus with a is equal to absolute value of a minus with b. For example, absolute value of negative 2 minus with 3 is equal to absolute value of 3 minus with negative 2, which is equal to 5. E absolute value of a multiplied with b is equal to absolute value of a multiplied with absolute value of b. For example, absolute value of 3 multiplied with negative 2 is equal to absolute value of 3 multiplied with absolute value of negative 2, which is equal to 6. F absolute value of a is divided by b is equal to absolute value of a is divided by absolute value of b. For example, absolute value of 3 is divided by negative 2, is equal to absolute value of 3 is divided by absolute value of negative 2, which is equal to 3 over 2. (2.2a) Solving absolute equations. For absolute value of x is equal to p, then it is equivalent to x is equal to p, or x is equal to negative p. Please bear in mind, here, we use the word or, as the relationship between the positive and negative parts, for absolute equation type of question. For example, if absolute value of x is 3, then it is equivalent to x is equal to 3, or x is equal to -3. The number line here represent the first definition of absolute values as we discussed before. Example 5. Solve the equation. Question A. Absolute value of x minus 3 is equal to 2. Solution A. As we discussed before, this absolute value is equivalent to x minus 3 is equal to 2, or x minus 3 is equal to -2. Then, we need to solve these two linear equations. And we get x is equal to 5, or x is equal to 1. For questions like this, we must test the answers first, before we finalize our answer. That is, by substitutes the value of x, for the answer we got earlier into the original function of the question. So, we will substitutes the value of x is equal to 1, to the function of absolute equation. As a result, this value of x is equal to 1, satisfied the absolute equation. Which is, absolute value of -2, is equal to 2. Then, 2 is equal to 2. Next, we will substitutes the value of x is equal to 5 to the function of absolute equation. As a result, this value of x is equal to 5, satisfied the absolute equation. Which is, absolute value of 2, is equal to 2. Then, 2 is equal to 2. So, both values of x are accepted. And our final answer are 1 or 5. We can write the final answer in form of set notation like this. Question B. Absolute value of 3x plus 5 is equal to 4. Solution B. This absolute value is equivalent to 3x plus 5 is equal to -4, or 3x plus 5 is equal to 4. Then, we need to solve these two linear equations. And we get x is equal to -3, or x is equal to -1/3. We must test the values of x first, before we finalize our answer. That is, by substitutes the value of x, for the answer we got earlier into the original function of the question. So, we will substitutes the value of x is equal to -3, to the function of absolute equation. As a result, this value of x is equal to -3, satisfied the absolute equation. Which is, absolute value of -4, is equal to 4. Then, 4 is equal to 4. Next, we will substitutes the value of x is equal to -1/3 to the function of absolute equation. As a result, this value of x is equal to -1/3, satisfied the absolute equation. Which is, absolute value of 4, is equal to 4. Then, 4 is equal to 4. So, both values of x are accepted. And our final answer are -3 or -1/3. We can write the final answer in form of set notation like this. 2.2a. Solving absolute equations. Question C. Absolute value of 2x minus with 3 is equal to 9 minus with x. Solution C. As before, we need to split the absolute value into negative value and positive value. Therefore, our absolute value will be 2x minus 3 is equal to negative, in brackets with 9 minus x. Or, 2x minus 3 is equal to positive, in brackets with 9 minus x. Then, we need to simplify these two linear equations, and solve it. And we get x is equal to -6, or x is equal to 4. We must test the values of x first, before we finalize our answer. That is, by substitutes the value of x, for the answer we got earlier into the original function of the question. So, we will substitutes the value of x is equal to -6, to the function of absolute equation. As a result, this value of x is equal to -6, satisfied the absolute equation. Which is, absolute value of -15, is equal to 15. Then, 15 is equal to 15. Next, we will substitutes the value of x is equal to 4 to the function of absolute equation. As a result, this value of x is equal to 4, satisfied the absolute equation. Which is, absolute value of 5, is equal to 5. Then, 5 is equal to 5. So, both values of x are accepted. And our final answer are -6 or 4. We can write the final answer in form of set notation like this. Question D. Absolute value of x plus with 5 is equal to 2x minus with 10. Solution D. Same step as before. After we split the absolute value, it is equivalent to x plus 5 is equal to negative, in brackets with 2x minus with 10. Or, x plus 5 is equal to positive, in brackets with 2x minus with 10. Then, we need to simplify these two linear equations, and solve it. And, we get x is equal to 5/3, or x is equal to 15. For questions like this, we must test the answers first, before we finalize our answer. That is, by substitutes the value of the answer we got earlier into the original function of the question. So, we will substitutes the value of x is equal to 5/3 to the function of absolute equation. As a result, this value of x does not satisfy the absolute equation, where the value we get is different in terms of sign, which is +20/3 is not equal to -20/3. So, we do not accept the answer that the value of x is equal to 5/3. NA stand for not accepted. Next, we will substitutes the value of x is equal to 15 to the function of absolute equation. As a result, this value of x satisfies the absolute equation, which is, absolute value of 20 is equal to 20. Then, 20 is equal to 20. So, our final answer is 15 only. We can write the final answer in form of set notation like this. 2.2a, Solving absolute equations. Example 5. Solve the equation. Question E. Absolute value of x squared plus with 3x and minus 8, is equal to 2. Solution for question E. As we discussed before, this absolute value is equivalent to x squared plus with 3x and minus 8, is equal to -2, or x squared plus with 3x and minus 8, is equal to +2. Meaning that, we already split the absolute value into positive and negative. Then, we need to solve these two quadratic equations. Here, we need to factorize the quadratic equation and solve the x values. If not, then we need to use a quadratic formula. And here is the answer. Since the absolute value is quadratic, then we will get our final answer of 4 values. And the answers is like this. Or, we can write the final answer in form of set notation like this. Question F. Absolute value of x squared plus with 6x and plus 3, is equal to 5. Solution for question F. As before, we need to split this absolute value into negative value and positive value. Therefore, our absolute value will be, first, x squared plus with 6x and plus 3, is equal to negative 5. Second, x squared plus with 6x and plus 3, is equal to positive 5. Then, we need to factorize the quadratic equation and solve the x values. If not, we have to use a quadratic formula. And here is the answer. Since the absolute value is quadratic, then we will get our final answer of 4 values. And the answers is like this. Or, we can write the final answer in form of set notation like this. Question G. Absolute value of x plus with 3, is equal to, absolute value of, 2x minus with 1. Solution for question G. Same step as before, we need to split the absolute value into negative value, and positive value. Therefore, our absolute value will be, first, x plus with 3, is equal to negative, in brackets with 2x minus with 1. Second, x plus with 3, is equal to positive, in brackets with 2x minus with 1. Then, we need to solve these two linear equations. And we get, x is equal to negative 2 over 3, or, x is equal to 4. We can write the final answer in form of set notation like this. Question H. Absolute value of 5 minus with 2x, is equal to, absolute value of, x plus with 8. Solution for question H. Same step as before, after we split the absolute value, it is equivalent to, first, 5 minus with 2x, is equal to negative, in brackets with x plus 8. Second, 5 minus with 2x, is equal to positive, in brackets with x plus 8. Then, we need to solve these two linear equations. And we get, x is equal to 13, or, x is equal to negative 1. We can write the final answer in form of set notation like this. 2.2 C. Solving inequalities of the forms. A. Absolute value of x is less than p. For example, absolute value of x is less than 3. For this kind of absolute value it is equivalent to x is between negative p and positive p. And then, we can split it into x greater than negative p and x less than p. Please bear in mind, here, we use the word and, as the relationship between the positive and negative parts. We can represent this absolute value with the number line, like this. Here, we must use empty circle to represent the number is not including. B. Absolute value of x is less than or equal to p. For example, absolute value of x is less than or equal to 3. For this part, it is the same as part A above. The only difference is less than or equal to. It means that the number is including. Here, we must use dense circle to represent the number is including. We can represent this absolute value with the number line, like this. C. Absolute value of x is greater than p. For example, absolute value of x is greater 3. For this kind of absolute value, it is equivalent to x is less than negative p, or, x is greater than p. Please bear in mind, here, we use the word or, as the relationship between the positive and negative parts. We can represent this absolute value with the number line, like this. Here, we must use empty circle to represent the number is not including. D. Absolute value of x is greater than or equal to p. For example, absolute value of x is greater or equal to 3. For this part, it is the same as part C above. The only difference is greater than or equal to. It means that the number is including. Here, we must use dense circle to represent the number is including. We can represent this absolute value with the number line, like this. Example 6. Solve by using properties of inequalities in A. Question A. Absolute value of x is less than 2. Solution for question A. Based on our concept learning before, absolute value less than for this question is equivalent to x is in between with -2 and +2. Question B. Absolute value of 3x plus 5 is less than 4. Solution for question B. Based on our concept learning before, absolute value less than for this type of question is equivalent to 3x plus 5, is in between with -4 and +4. Then, we must simplify the inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. And the final answer can be written in the set notation like this. Which is, x is in between with -3 and 1/3. Example 6. Solve by using properties of inequalities in B. Question C. Absolute value of 2x minus with 3 is less than or equal to 9. Solution for question C. Based on our concept learning before, absolute value less than or equal to for this type of question is equivalent to 2x minus with 3, is in between and inclusively with -9 and +9. Then, we must simplify the inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. And the final answer can be written in the set notation like this. Which is, x in between and inclusively with -3 and 6. Question D. Absolute value of 7 minus with 3x is less than or equal to 2. Solution for question D. Based on our concept learning before, absolute value less than or equal to for this type of question is equivalent to 7 minus with 3x, is between and inclusively with -2 and +2. Then, we must simplify the inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. And the final answer can be written in the set notation like this. Which is, x in between and inclusively with 5/3 and 3. Example 7. Solve by using properties of inequalities in C. Question A. Absolute value of x is greater than 2. Solution for question A. Based on our concept learning before, absolute value greater than for this type of question is equivalent to x is less than -2 or x is greater than +2. Question B. Absolute value of 3x plus 5 is greater than 4. Solution for question B. Based on our concept learning before, absolute value greater than, for this type of question is equivalent to 3x plus 5 is less than -4 or 3x plus 5 is greater than +4. Then, we must simplify the inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. And the final answer can be written in the set notation like this. Which is, x is less than -3 or x is greater than -1/3. Example 7. Solve by using properties of inequalities in D. Question C. Absolute value of 2x minus with 3 is greater than or equal to 9. Solution for question C. Based on our concept learning before, absolute value greater than or equal to for this type of question is equivalent to 2x minus with 3 is less than or equal to negative 9, or 2x minus with 3 is greater than or equal to positive 9. Then, we must simplify the inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. And the final answer can be written in the set notation like this. Which is, x is less than or equal to negative 3 or, x is greater than or equal to positive 6. Question D. Absolute value of 7 minus with 3x, is greater than or equal to 2. Solution for question D. Based on our concept learning before, absolute value greater than or equal to for this type of question is equivalent to 7 minus with 3x is less than or equal to negative 2, or 7 minus with 3x is greater than or equal to positive 2. Then, we must simplify the inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. And the final answer can be written in the set notation like this. Which is, x is less than or equal to 5 over with 3 or, x is greater than or equal to positive 3. Example 8. Solve. Question A. Absolute value of x plus 1 is greater than or equal to 3x minus with 1. Solution for question A. Based on our concept learning before, absolute value greater than or equal to for this type of question is equivalent to x plus 1 is less than or equal to negative in brackets with 3x minus with 1, or x plus 1 is greater than or equal to positive in brackets with 3x minus with 1. Then, we must simplify these two inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. After the inequality is over, we need to use the number line concept to determine the final answer like this. And the final answer can be written in the set notation like this. Which is, x is less than or equal to 1. Question B. Absolute value of 2x plus with 5 is greater than x minus with 3. Solution for question B. Based on our concept learning before, absolute value greater than for this type of question is equivalent to 2x plus 5 is less than negative in brackets with x minus with 3, or 2x plus 5 is greater than positive in brackets with x minus with 3. Then, we must simplify these two inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. After the inequality is over, we need to use the number line concept to determine the final answer like this. And the final answer can be written in the set notation like this. Which is, x is all real number. Example 8. Solve. Question C. Absolute value of x minus with 3 is less than 2x plus with 1. Solution for question C. Based on our concept learning before, absolute value less than for this type of question is equivalent to x minus 3 is in between with negative in brackets with 2x plus 1 and positive in brackets with 2x plus 1. Then, we must simplify these two inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. After the inequality is over, we need to use the number line concept to determine the final answer like this. And the final answer can be written in the set notation like this. Which is, x is greater than 2 over 3. Question D. Absolute value of 5x minus with 2 is less than or equal to x plus with 5. Solution for question D. Based on our concept learning before, absolute value less than or equal to for this type of question is equivalent to 5x minus with 2, is in between and inclusively with, negative in brackets with x plus 5 and, positive in brackets with x plus 5. Then, we must simplify the inequalities by make it coefficient of x is single. Solve the compound inequality based on our concept learning before. After the inequality is over, we need to use the number line concept to determine the final answer like this. And the final answer can be written in the set notation like this, which is x in between and inclusively with negative 1 over 2 and 7 over 4.
Chapter 3, Sequences. What is a sequence? A sequence is a set of things, usually numbers, that are in order. For example, 3, 5, 7, 9 and so on. 3 we called first term. 5 is second term. 7 is third term. 9 is fourth term. And 3 means goes on forever, or we called infinite. Term, element, or member mean the same thing.
If the sequence goes on forever, it is called an infinite sequence. Otherwise it is a finite sequence. For example, 1, 2, 3, 4, and so on, is a very simple sequence, and it is an infinite sequence. 20, 25, 30, 35, and so on, is also an infinite sequence. 1, 3, 5, 7, is the sequence of the first 4 odd numbers, and is a finite sequence. 4, 3, 2, 1, is 4 to 1 backwards. 1, 2, 4, 8, 16, 32, and so on, is an infinite sequence where every term is double. A, B, C, D, E, is the sequence of the first 5 letters alphabetically. F, R, E, D, is the sequence of letters in the name Fred. 0, 1, 0, 1, and so on, is the sequence of alternating zeros and ones. Yes, they are in order. It is alternating order in this case. When we say the terms are in order, we are free to define what order that is. They could go forwards, backwards, or they could alternate, or any type of order you want. For example, 0, 1, 0, 1, 0, 1, and so on is the sequence of alternating zeros and ones. The set would be just 0 and 1. We write in curly bracket. Another example, the sequence 3, 5, 7, 9, and so on, starts at 3 and jumps every 2 times. That's why we can see the difference between two numbers is 2 units. The nth term of a sequence is denoted by Tn and is called the general term. A sequence can be fully defined by its general term. For example, find the general term of the sequence 1, 3, 5, 7, and so on. The solution: first we write T1 equal to 1. T2 equal to 3. T3 equal to 5. From the sequence we know that it's jumped by 2 unit. So we can write T1 equal to 2 multiplied 1 and plus or minus with any number. Same also with T2 equal to multiplied 2 and plus or minus with any number. Last T3 equal to multiplied 3 and plus or minus with any number. So you must think how to get equal number from the sequence. The conclusion is minus with 1. Lastly we can write the general term Tn equal to n minus 1.
Example 1b. Find the general term of the sequence 4, 7, 10, 13 and so on. First we write T1 equal 4, next T2 equal 7, T3 equal 10. From the sequence, we can see the difference between first and second number is plus 3. So we can write T1 equal 3 times 1, plus or minus, with unknown. T2 equal 3 times 2, plus or minus, with unknown. T3 equal 3 times 3, plus or minus, with unknown. So, we can think either we must add, or minus with any number, to give same sequence from the question. The conclusion we plus with 1. Finally we can write n term, Tn, equal 3n plus 1. Example 1c. Find the general term of the sequence. 1, 1 over 3, 1 over 5, 1 over 7, and so on. First we write T1 equal 1 over 1, because most of the sequence in fraction. Next T2 equal 1 over 3, T3 equal 1 over 5. From the sequence, we can see the numerator are the same, but denominator had difference by plus 2. So, we can write T1 equal 1 over 2 times 1, plus or minus, with unknown. T2 equal 1 over 2 times 2, plus or minus, with unknown. T3 equal 1 over 2 times 3, plus or minus, with unknown. So, we must think, either we must add, or minus with any number, to give same sequence from the question. The conclusion we minus with 1 at denominator. Finally we can write n term, Tn, equal 1 over 2 times n minus 1. Example 1d. Find the general term of the sequence. 1 square, 2 square, 3 square, 4 square, and so on. First we write T1 equal 1 square. Next T2 equal 2 square. T3 equal 3 square. From the sequence, we can see the power are the same, but the number in ascending order start with 1. So, the conclusion we can write n term, Tn, equal n square.
Example E. Find the general term of the sequence. 1 over 2 times 3. 2 over 3 times 4. 3 over 4 times 5, and so on. First we write T1 equals 1 over 2 times 3. T2 equals 2 over 3 times 4. T3 equals 3 over 4 times 5. From the sequence, we can see the numerator are ascending order. But denominator have to part. First part start with 2 and increase by 1 unit. Second part start with 3 also increase by 1 unit. So we can write T1 equals 1 over 1 plus or minus any number, times 1 plus or minus any number. T2 equals 2 over 2 plus or minus any number, times 2 plus or minus any number. T3 equals 3 over 3 plus or minus any number, times 3 plus or minus any number. So we have to think about whether it is necessary to add or subtract any number to get the same as the sequence. Conclusion: we plus 1 for first part, plus 2 for second part at denominator. Finally, we get Tn equals n over n plus 1 times n plus 2.
Example 1f. Find the general term of the sequence. -3, 9, -27, 81, and so on. First we write T1 equal -3. Next T2 equal 9. T3 equal -27. From the sequence, we can see the alternate sign. Start with negative, and next, with positive, and so on. If sequence with alternate sign, we apply -1 to the power of 1, if the sequence start with negative. Because, when -1 to the power odd number, it become negative. We apply -1 to the power of 2, if the sequence start with positive. Because, when -1 to the power even number, it become positive. So, we can write T1 equal -1 to the power of 1 times with 3. T2 equal -1 to the power of 2 times with 9. T3 equal -1 to the power of 3 times with 27. 3, 9, 27. Not in sequence form yet, so we can apply index rules. We can write T1 equal -1 to the power of 1 times with 3 to the power of 1. T2 equal -1 to the power of 2 times with 3 to the power of 2. T3 equal -1 to the power of 3 times with 3 to the power of 3. Finally, we can find the n term. Tn equal -1 to the power of n times with 3 to the power of n. Or we can write -3 to the power of n. Arithmetic sequence is a sequence whose consecutive terms have a constant difference. Giving formula, n term, is Tn equal a plus n minus 1 times with d. A is called the first term, and d is called the common difference. It can be positive, negative or zero. Arithmetic series. The sum of an arithmetic sequence is called an arithmetic series. Giving formula, sum of the first n term is Sn equal n over 2 times with 2a plus n minus 1d, or Sn equal n over 2 times a plus l, where l equals last term. We also can find the n term by using formula Tn equal Sn minus Sn minus 1.
Example 2. Given 2, 5, 8, and so on. Find the fourth term by using Tn and Sn formula. Solution. From the sequence, we can find a equals 2. D equals 5 minus 2. So equals 3. To find T4 using Tn formula, from Tn equals a plus n minus 1 d. Substitute a equals 2 and d equals 3. T4 equals 2 plus 4 minus 1 times 3, we get equals 11. To find T4 using Sn formula, from Sn equals n over 2 times 2a plus n minus 1 d. First find S4, so equals 4 over 2 times 2 times 2 plus 4 minus 1 times 3 equals 26. S3 we can find from the sequence by adding the term 2 plus 5 plus 8 equals 15. So T4 equals S4 minus S3. 26 minus 15 equals 11. Example 3. The second and seventh terms of an arithmetic sequence are -5 and 10 respectively. Find the eighth term and common difference. The solution is: first, write T2 equals -5. T7 equals 10. Using n term formula, T2, a, plus 2 minus 1, d, equals -5. T7, a, plus 7 minus 1, d, equals 10. Then, simplify, we get a plus d equals -5, let as equation 1. Second, a plus 6d equals 10, let as equation 2. Using simultaneous equation concept, equation 1 minus equation 2, we get 0, minus 5d equals -15. Then we can find d equals 3. Next, from equation 1, we can find the value of a. A plus 3 equals -5. So, a equals -8. Last, we can find a term by using formula n term. T8 equal -8 plus 8 minus 1 times 3, so equal 13.
Example 4. Find the sum of all the odd numbers between 0 and 500 which are divisible by 7. The solution. First we write the sequence start with 7, 14, 21, 35, and last with 497. The question asks only odd number. So, we finalize and get 7, 21, 35, and last with 497. From the sequence, A equals 7, D equals 21 minus 7 equals 14. Using formula, Tn equals A plus n minus 1 times D. So, 497 equals 7 plus n minus 1 times 14. We can simplify, become 490 over 14 equals n minus 1. So, we can solve, n equals 36. Last, to find sum of the first 6 term, using formula, S6 equals 36 over 2 times with 7 plus 497. So we get the answer, 9072. Example 5. Show that the sequence with sum of the first 10 term, Sn, equals 3n squared plus 5n, is an arithmetic sequence. Find the first term and the common difference. The solution
If the sequence is an arithmetic sequence, then we have to show that Sn equals n over 2 times 2a plus n minus 1 d. From the question, given Sn equals 3n squared plus 5n. First, we factorize n over 2 and multiply it with 6n plus 10. Next, we minus 6 and plus 6 after 6n. The reason we plus and minus 6 to create n minus 1. After that, we factorize 6n minus 6, become 6 times n minus 1. It become n over 2 times 6 times n minus 1 plus 16. Last, we try to compare with Sn formula. We get n over 2 times 2 times 8 plus n minus 1 times 6. So, final answer, A equals 8, D equals 6. Example 6. The second term of an arithmetic sequence is 2 times the fourth term and the difference of the eighth term and the third term is minus 20. Find the first term and the common difference. The solution. From the question, given t2 equals 2 times t4, we let as a first equation. And t8 minus t3 equals minus 20. Let as a second equation. From first equation, a plus d equals 2 times a plus 3d. Expand, we get a plus d equals 2a plus 6d. After we simplify, we get a equals minus 5d. Let as a first equation. From second equation, a plus 7d minus a plus second equal minus 20. Simplify, we get 5d equal minus 20. So, d equals minus 4. Last, we substitute d equals minus 4 into first equation. We get answer, a equals 20. Example 7. In an arithmetic sequence, the sum of the first two n terms is equal to the sum of the following n terms. If the first term is 12 and common difference is 3, find the value of n. The solution. From the question, given s2n equals s3n minus s2n, and given a equals 12, d equals 3, we simplify, we get 2s2n equals s3n. From the Sn formula, we substitute 2n into n, it become 2n over 2 times 2a plus 2n minus 1 d. Then s2n multiplied with 2 and substitute a equals 12 and d equals 3. After we simplify, we get 2s2n equals 2n times 6n plus 21. Let us equation 1. Next, for s3n, we substitute 3n into n, it become 3n over 2 times 2a plus 3n minus 1 d. Substitute a equals 12, d equals 3. Simplifying become s3n equals 3n over 2 times 9n plus 21. Let us equation 2. Equation 1 equals equation 2. 2n times 6n plus 21 equals 3n over 2 times 9n plus 21. We simplify until form quadratic equation. 3n square minus 21 equals 0. And then factorize. We get the answer n equals 0 and n equals 7. Final answer is n equals 7.